We are now ready to take a closer look at the common ion effect in video 3.3.2. Okay, so our common ion effect. Let's look at this through some examples. Like we're again going to use calcium hydroxide, and it's placed this time in a solution that already contains some base, so 0.15 molar sodium hydroxide. So sodium hydroxide, of course, is going to release hydroxide ions into solution because it's a base. Okay, our dissociation equation for the dissolution of calcium hydroxide is calcium hydroxide, which is a solid. So calcium ions plus hydroxide ions, and that's aqueous. To calculate the molar solubility of calcium hydroxide in the sodium hydroxide solution. So we're going to do this the same way as we have been by using our ice table. So let's just go ahead and rewrite our equation. Okay, so solids don't count. So at the beginning, we don't have any calcium, but we do have some hydroxide. So here, we have 0.15 molar sodium hydroxide. So that means we have 0.15 molar OH minus from our sodium hydroxide there. That's what that's telling us. So here we're actually starting with something already in our solution, our 0.15 hydroxide. Okay, let's keep going. So here, this is going to be plus S plus 2S. This carries down. So we have S and then 0.15 plus 2S. Alright, let's set up our KSP equation just like we have before. So KSP equals concentration of our calcium ions times the concentration of our hydroxide ions squared. And now plugging the S's in our KSP for this. Our KSP was given to us on the previous problem, on the previous video. But just in case, I'm just going to go ahead and write that here. So KSP is equal to 1.3 times 10 to the negative 6. And that was from, again, the previous problem, example 2. Since we're using the same compound. We know the KSP. So 1.3 times 10 to the negative 6 equals the calcium, which is S. And then here, 0.15 plus 2S squared. Now, we can FOIL this whole thing out, and we can use the quadratic equation, and we can solve it that way. However, we are going to assume that the amount of hydroxide that comes off this very sparingly soluble salt is not really that much. Because in reality, a sparingly soluble salt means that means there's not very many ions coming from it. We're going to say, and we're going to assume, that that amount that's added, the 2S, whatever comes off the calcium hydroxide, is nothing in comparison to the 0.15 molar that's already there. This is a huge amount compared to what's going to come off here. So we are going to assume that 2S is much, much, much less than 0.15 molar here. It's because of that, we can go ahead and cross off the 2S and pretend it's not even there. Because what it adds after you take into account sig figs, you're going to get the same answer anyway. You're just going to go through a whole lot more math. So, with that assumption, plugging everything in, all you have to do is take the 0.15 squared then here. You don't have to take into account that plus 2S anymore. You can go ahead and easily solve for S and get 5.8 times 10 to the negative 5 molar as your solubility. Alright, compare the solubility of calcium hydroxide in pure water, which is given here, with that in the NaOH solution. And the NaOH solution, which we just found here, is 5.8 times 10 to the negative 5 molar. Well, which solution is it more soluble in? In pure water or in the sodium hydroxide? So the answer is that it's more soluble in your pure water because you get a whole lot more ions being formed in the pure water. 6.9 times 10 to the negative 3rd molar. That's a much bigger number than 5.8 times 10 to the negative 5 molar. So this is more soluble in the pure water. Okay, example 3. What is the solubility of lead chloride in 0.1 molar sodium chloride solution? And here they're giving you the KSP of lead chloride. Okay, I would like you to pause the video now. This is just like the previous problem where you're going to make the same assumptions. Please pause the video and get all the way to S. Figure out what S is and then come back. Okay, so we're going to go ahead and start with our dissociation equation. So PbCl2, that's solid. That's in equilibrium with lead ions, Pb2+, AQ. And how can I tell that's 2+? Well, each of these are -1, so that must be +2, because that's a neutral compound. Plus my chloride, I have 2 of those. That's aqueous. Don't take into account my solid here. I have no lead to start with, but I do have sodium chloride, so now I have a source of chloride here. So I really have 0.1 molar of chlorine or chloride ions already in my solution. So I'm starting with 0.10 molar chloride. Plus S plus 2S. So this gives me S, and this is 0.1 plus 2S. Okay, that's my ice table. Setting up my KSP equation, KSP equals, well, just my products times each other, so Pb2 plus Cl minus squared from that coefficient. Plugging in my numbers, I have my KSP, 1.6 times 10 to the negative 5 equals S is here, times 0.10 plus 2S squared. Now again, I'm going to make that same assumption that this amount of chloride that comes off my very sparingly soluble lead chloride isn't very much compared to the 0.1 molar that's already in solution. So it's not really going to make a difference when I add it. So I'm going to cross that out and get my S equal to 1.6 times 10 to the negative third molar. So that's my molar solubility there. Now we're going to calculate the solubility of lead chloride in pure water and compare those solubilities. You can do another ice table if you like, or you can use that shortcut that you learned a couple videos ago. So I'm going to go ahead and use the shortcut. So let's see, PbCl2. So my Pb is just going to be S. Cl2, I know that's going to be 2S squared. So 2 is going to be here as well. And that's going to equal the KSP. I'm given the KSP up here, 1.6 times 10 to the negative 5. And you can only really do this in pure water. Okay, my S then is going to be equal to 0.016 molar. Okay, so here's my solubility in pure water. Here is my solubility in sodium chloride solution where there's a common ion. Which one is more soluble? Okay, so hopefully you said that the one in water is more soluble because this number is much bigger. Taking this out of scientific notation gives you 0.0016, right? So this number is much smaller than this number is here. So here, this is in pure water. You're much more soluble in H2O. So more soluble in H2O. Okay, example 4. Which of the following salts would be more soluble in an acidic solution? Now remember, acids donate H plus to solution, right? They donate H plus ions to solution. So here, if you added an acid to your zinc carbonate, the H plus isn't going to react with the zinc because it's going to be positively charged, but your carbonate is going to be negatively charged. So you're actually going to form some HCO3, some carbonic acid there. I want you to go ahead and pause the video and see what you would form for each of these compounds. Okay, so hopefully for this one you saw you would make HF, it would interact with the fluorine. Here, HCl. Here, H3PO4. Here, HI. And then finally here, HOH, which is the same thing as H2O. Okay, so let's see what each of these are. Which of the following would be more soluble in an acidic solution? So this is a weak acid. This is a weak acid. Strong acid, weak acid, strong acid, weak acid. H2O can be a weak acid or a weak base. In this case, we're going to treat it like it's a weak acid because we have all acids here. So, since this HCO3 doesn't break up in solution anymore, it's not going to form any more ions. So basically, this is going to pull ions out of solution. So let's say it was like, I don't know, let's say these are carbonate. You're going to pull some ions out of solution. So your reaction is going to shift toward more ions, thanks to Le Chatelier's principle. And your solid's going to break up more. So if you're sequestering ions from your solution, that means the solubility is going to increase. So this salt would be more soluble. So I'm going to go ahead and highlight this one. I want you to determine which other salts would actually form compounds that don't break up again and pull ions out of solution. Please pause the video and do that now. Okay, so if we form hydrofluoric acid, HF, that's going to pull those negatively charged fluoride ions out of your solution, and that's going to increase in solubility. HCl, you're going to pull those Cl, those chloride ions out of solution, but here you're actually going to have your HCl immediately dissociate into H plus and Cl minus. Because this is a strong acid, it dissociates 100%. So you get lots and lots more, you get those chloride ions right back. So you're actually not going to be able to increase your solubility here, because although you're forming HCl momentarily, you immediately form the ions again. So you really don't pull those chloride ions out of solution. Next one, H3PO4, phosphoric acid. Yes, that would increase in solubility because that's a very weak acid, so they tend to stay together. HI, strong acid again. So really what's happening here is you're going to get H plus iodide ions there. So you're not really pulling those iodide ions out of solution. They're not staying together with the HI, so it's not going to increase your solubility. Here, H2O, well, that's going to stay together. That's a very weak acid, the weakest you can get. And that is going to make sure those hydroxide ions stay out of solution and they're bound up in water. So come up with a rule to quickly determine how you could tell. So you could see that all the ones that are highlighted have in common that they're weak acids. So, or the salts rather. So this is a salt. Salt is any positive and negative, right? So the salts with anions, the negative ions, of weak acids, so that means if you put a hydrogen ion with it, it's going to form a weak acid like we saw here. Salts with anions of weak acids are more soluble in an acidic solution. Salts with anions of weak acid are more soluble in acidic solution. Okay, so that's our rule that we came up with after figuring out why that is the case up here. Okay, next time we'll look at selective precipitation, but that is it for video 3.3.2.